Welcome back, everybody. Mr. Johnson to you, coming from my dad's house in Sammamish. He got a knee replacement last week, so I'm staying with him, taking care of him, putting lots of ice packs on his knees, helping him with his PT, and spending 10 hours a day, or 12, staring at a computer screen. Good times on October 27th. Anyways, this is Lecture 14, Part 2, Enthalpy as it pertains to heats of formation and the law of Hess, or Hess's Law. We are on page 209 of your ebook in section 4.5, Enthalpy. And the first thing I'd like us to pay attention to is this highlighted sentence in green, which reminds us, I did mention this in our last lecture, that there's a number of ways for calculating overall enthalpy changes in an AP chemistry student should be familiar with. I've got a chart here that is going to suggest there's two ways, but it says the three most common are the law of Hess, the use of tabular heats of formation, the use of bond energies. The last lecture was about using bond energies. This lecture is about using heats of formation and the law of Hess. I'm going to take you to that flow chart. So we hopefully already know that enthalpy, abbreviated delta H, or the change in heat or the change in enthalpy, is the energy change, always in kilojoules per mole of reaction for a process or a reaction. I would argue there's two primary ways to determine enthalpy. One of those two primary ways is from theoretical values, and that's what the sentence in our book was about. There's three ways to determine enthalpies from theoretical values. One of those ways we know about is bond energy. One of those ways we're going to learn about today is called Hess's Law. One of those ways is using what's called heats of formation, and that's also what today's lecture is going to be about. And then the other main way, the experimental method to determine enthalpy, is based on what's called calorimetry. Calorimetry. And if you remember from prior science classes, and if not, it's fine, I'll teach it to you. Calorimetry, he's using that equation, that Q equals MC delta T equation, which Jackie Maurice was talking about today in class. Looking forward to this lecture. So again, today is about using Hess's law to determine to determine enthalpy, and using heats of formation to determine enthalpy. And then next week, all of next week, and the week after a little bit, is going to be the experimental method using what's called calorimetry. I've scrolled down. I'm still on page 209 of the ebook, or 201 of the textbook. We can skip this stuff at the top if we want. This is all information and theory we know. I'm focusing on this phrase here at the bottom, which is this process I'm going to teach you about, this method or technique called the law of Hess, or Hess's law of heats of summation. And what that law says, which won't make sense yet, it will in a moment, is that the enthalpy change of a reaction is expressed as the algebraic sum of the enthalpy changes of a series of other reactions that have been manipulated to produce the overall reaction. That was a mouthful. You'll never be asked to state what Hess's law is, rather just how to use it. And so that's what I'd like to show you now, is how to use Hess's law. So we've flipped the page, we're on 210 of the ebook, and we're looking at this section here at the top. When you are asked to use Hess's law, it should be fairly obvious to you, because you're going to see that they look very similar. Hess law problems look similar. There's always a reaction, an overall reaction, that you're trying to figure out what the delta H is. So our goal is to figure out the delta H of this reaction. And if it's a Hess law problem, you'll always be given a series of two or more reactions whose delta H's are given to you and that can be manipulated and summed algebraically to give you this overall reaction, and therefore its enthalpy or its delta H. So this is a fairly prototypical looking Hess law problem. When you're given a Hess law problem, the reactions that are supposed to be used algebraically to give you the overall reaction will always work. So it'll always work out. And I'm going to walk you through what that means and how it'll work out here in just a moment. So here's how I approach a Hess law problem. I look first at the overall reaction, whose delta H it is I'm trying to figure out. This is the one down here. And I start on the reactant side and say to myself, okay, I need carbon on the reactant side and hydrogen on the reactant side, and then I need methane on the product side. Then I go up to the reactions that I'm given that will sum algebraically with cancellation to give me this reaction, and I find which reaction has carbon in it. And that's reaction 2. I also look to see that the carbon in reaction 2 is already on the reactant side. And it is. Notice that the carbon in reaction 2 is on the reactant side. I also look to see that the coefficient in front of carbon, which is already on the reactant side, is the same as it needs to be in the overall reaction, and that is the case as well. So you'll In a moment, hear me say that reaction 2 doesn't need to be manipulated. It has carbon on the reactant side, and there's just 1 mole of carbon, or 1 carbon, which is what I want in the overall reaction. So now I'm going to look for hydrogen in any of these reactions above. And it looks like hydrogen is in reaction 3. Reaction 3. It has hydrogen already on the reactant side, which is my goal, but it only has 1 hydrogen, or 1 mole of hydrogen, and not 2. Hang on to that for a moment. It has it on the reactant side, great, but it has 1 mole of hydrogen, not 2. That's a problem. We need to manipulate it. I need methane in one of the reactions above, which is in reaction 1, but it's on the reactant side in reaction 1 and not on the product side. But I need it on the product side. The coefficient is okay, but it's in the reactant side in the above reaction, but I need it on the product side. So we're now going to scroll down to see how those reactions above were manipulated to give us what it was we wanted. Remember, the second reaction is already good. The third reaction needs 2 hydrogens in it, not 1. And the first reaction needs methane on the product side and not the reactant side. So as we scroll down, we see reaction 1 written exactly as it was above. There's no change to reaction 1. But notice that the second reaction down below is this third reaction that has been multiplied by 2. Everything in that third reaction has been doubled. And as I scroll down, I see that that's the case. There's 2 H2s, 1 O2 instead of a half, and 2 H2Os. And notice that the delta H of that reaction was also doubled, which is something that we've learned. When you double everything in a reaction, the delta H also has to be doubled. If you remember, reaction 1 had methane on the reactant side, but we needed it on the product side. So the entire reaction has been flipped around, or we've multiplied the entire reaction by -1. And notice that down here in this third reaction, that's happened. What was the reactants are now the products. What were the products are now the reactants. And the delta H has had its sign flipped. It was -891 up top, and it's +891 down below. So once the reactions have been manipulated, which had to happen to 2 of them, and we just spoke about which and why, then you cancel out any species or substances that are the same on 2 sides of any 2 reactions. So let's look at how that appears here. Notice that carbon dioxide is a product in this reaction. It's a reactant in this reaction. And kind of like in math, if you're adding up a series of equations, you can cancel out things on opposite sides of any 2 equations. That's happened to carbon dioxide. It was already canceled out. The same has happened for water. We got 2 waters on the product side, 2 waters on the reactant side. Those were already canceled out. And then we had 2 oxygens on the product side here, and a total of 2 here, which were also canceled out. And what we're left with, which was the goal, was 1 mole of carbon on the reactant side, 2 moles of hydrogen on the reactant side, and 1 mole of methane on the product side. And everything else that we didn't want left in the overall reaction has been canceled. Now, what we just saw was equations being manipulated to give us the overall desired equation, and them being summed algebraically with cancellation to give us the overall reaction. What then the final step of Hess's law is you take those enthalpies of the reactions that were manipulated and summed algebraically to give you the overall reaction, and you just add their enthalpies up. We just add these numbers up, and the sum of the enthalpies of these 3 reactions will give us the enthalpy of the overall reaction that we are interested in finding. Remember, though, we had to double the reaction in the middle to get 2 H2s, and we had to flip the sign of this last one. And that's already happened, which I mentioned a bit ago. So the overall enthalpy of the reaction above is -75 kilojoules per mole. That's Hess's law, and we'll do a couple more as practice. So it's been about 30 minutes since I saw you last. My mic went out. I got super mad at my computer. I've calmed down, and we're back. So I'm on page 211 of the ebook. I flipped a page, 203 of the textbook, and we're going to do this practice problem here at the bottom of this page. I'm going to take you to the whiteboard, because here we go. Here is how, once again, I approach a Hess Law problem. I'm looking at the reaction that I am overall trying to find the enthalpy of, knowing that these 2 reactions down below will sum after manipulation and cancellation into this reaction above. So I look at the first reactant that I want to make sure I end up with, which is the NOCl. In fact, there's only one reactant. And I notice that it's in reaction 2. I notice that the NOCl in the second reaction down below is on the product side. I need it on the reactant side, so that means I actually need to flip this reaction. And I notice that there's one of them on the product side in this reaction below, or 1 mole of it and not 2. So what I need to do is flip and double this second reaction. And how I indicate that my intent to flip and double a reaction is to write -2. That's the flipping and doubling. So I'm going to flip and double that, and when I do that, I end up with 2 NOCl's reacting to form 2 NOs, and then just 1 chlorine, because half times 2 is 1 chlorine gas. The delta H also needs to be doubled and the sign flipped. So when I double 38.6 and flip the sign, I get positive 77.2 kilojoules per mole. All right, looking good. So then I go to the product side of my reaction I'm trying to find, and I notice that I need nitrogen and oxygen and chlorine on the product side. Well, I already have the chlorine on the product side from having flipped this first reaction. And it's Cl2, not Cl, I'm noticing. I made a little typo there, it's Cl2. But I need N2 and O2 on the product side. Well, this first reaction has N2 and O2 in it, but it has 1 of each, and they're on the reactant side, excuse me, a half of each. So I need to flip and double that first reaction as well, because I need 1 N2 and 1 O2 on the product side, which flipping and doubling will achieve. So then I get 2 NOs yielding an N2 and an O2. And when I flip and double the delta H for that, -2 times 90.3 is -180.6 kilojoules per mole. All right, so let's see what happens when we cancel things out of both sides and sum these equations. Usually things will cancel once you've done the proper manipulation to the equations that need to be done. Let's hope that that happens here. Looks like it will. If I cancel NO from the reactant side of reaction 2 and the product side of reaction 1, I am left with NOCl, which I wanted on the reactant side, N2 and O2 on the product side, and then Cl2 on the product side as well. Ooh, lots of fancy colors here. So at this point, I write the overall reaction that I'm left with, which is going to be 2 NOCl's yielding N2 gas, O2 gas, and Cl2 gas. And the enthalpy of this reaction will be the sum of the enthalpies of the 2 reactions that added up algebraically to give us this overall reaction. If I add 77.2, bear with me for a second, to -180.6, I get, oops, syntax error, 77.2. I can do it, 0.2 minus, no, I am struggling. Still mad at my computer. -180.6. I get -103.4. Sorry for the delay. -1. 1. Oh, rough time. -103.4 kilojoules per mole. All right, so there was a nice example problem of Hess's Law. We'll do one more together, and then we'll move on to heats of formation. So we've flipped to 212 of the ebook, or 8 pages minus that in the textbook, and we're doing practice problem 3 here, down at the bottom of the page. Mr. Johnson's getting tired. We're going to go back to the whiteboard and solve this one. I recommend you try this on your own right now. This one's a bit tricky. Try this one on your own. When you're done, come back and check out the solution that I've provided for you. Try this one on your own. Pause the video. So here's what I've done so far. I'm looking at this overall reaction that these reactions will sum algebraically to after manipulation and cancellation to find the delta H of, and I notice that I want NO on the reactant side and just 1 mole of NO. This third reaction has NO on the reactant side, nothing else does, there's 1 mole of it, so I'm going to keep it. This check mark is saying, hey, I'm going to keep that one. Then I need 1 mole of O atoms, individual O atoms, which are rare. It's a very reactive species. It's a free radical. Oxygen is usually O2. But on the reactant side, and just 1 mole of it. It's the second reaction that has individual O atoms in it, but they're on the product side, and there's 2 moles of it, not 1. So I need to flip that and have it. I'm going to multiply it by negative 1/2 to get the O atoms on the left and for there to be a reduction of them from 2 to 1. So I'm flipping it and having it. And then I need NO2 on the product side, which there is already 1 mole of on the product side in reaction 3. So that's looking pretty good. So then my thought is, well, what's up with reaction 1? It's got ozone, O3 in it, and oxygen in it. Those molecules must end up getting canceled because they're not in the overall reaction. So I thought to myself, well, I see ozone here in the third reaction that doesn't show up in the overall reaction. It's going to need to cancel. And so it must be that this first reaction will cancel those ozones in the third reaction. For those to cancel, they'd need to be on the product side, and there'd need to be 1 mole of them, not 2, to cancel these 1 mole of ozone molecules down here. So I flipped and halved the top reaction as well for ozones to cancel. And what you'll find is it also takes care of the O2 or the oxygen cancellation. I could have thought of reaction 1 in terms of oxygen. I just went for it in terms of ozone. So I've rewritten reaction, 2 by this is reaction 1, having flipped and halved it. This is reaction 2, having flipped and halved it as well. And this is reaction 3, not having been changed. So I started to cross some things out, and then I wanted to wait so you could see it because that's so exciting. Ozones I've crossed out as a reactant and a product. Looks like I have 1.5 moles of oxygen on the left here, and then I have 1/2 mole of oxygen and a mole of oxygen on the product side here. So those are going to cancel as well. The 1.5 moles of oxygen will cancel the 1.5 moles of oxygen. And am I left with anything else? I've got NO and oxygen yielding NO2. So I've got my overall reaction, NO plus O yields NO2, and the delta H is going to equal the sum of those numbers, which is negative 233 kilojoules per mole. I chose not to do the calculation live, so you didn't have to see me suffer through multiple syntax errors again. All right, so there is our second and final practice problem with Hess's Law. Hopefully that makes sense. We're going to move on to heats of formation now and be done shortly. So we've scrolled back in our book. We're on page 209 of the ebook, and we're taking a look now at this highlighted section in yellow up here about heats of formation. So this last part of this lecture is about how we use the heats of formation, you don't know what those are yet, to calculate the enthalpy of a reaction, knowing that we already have 2 other ways to do that. One is using bond energies, bond enthalpies, and the other, what you just learned, using Hess's Law, or the law of Hess. So this sentence, which won't make total sense yet, says that it's important to recognize that the change in heat of formation, the enthalpy of formation, and there's a little superscripted O up there, it's called naught. We'll talk about that in a moment. Abbreviated delta HF naught, the heat of formation naught, is really just the heat of a reaction for a chemical change involving the formation of a compound from its elements in their standard states. The heat of formation is the enthalpy change for a reaction where a mole of a substance is formed from its elements in their standard states. Heat of formation is the energy change associated with forming 1 mole of a substance from its elements in their standard states. And in this case, standard state, not STP, SATP refers to the state or phase an element exists under conditions defined by convention as standard, SATP. Whereas STP, which we will talk more about in our gas law unit, whereas STP is 0 Celsius or 273 Kelvin and 1 atmosphere or 101.3 kilopascals. We'll talk about pressure later. SATP is not 0 Celsius, it's 25 degrees Celsius. And then 1 atmosphere pressure for gases, or 101.3 kilopascals if we want to use that unit. And if we're dealing with aqueous substances, it's 1 molar, 1 mole per liter. And all that will make more sense later. Again, SATP, or standard state conditions, is 25 degrees Celsius, 1 atmosphere, and if a solution is involved 1 molar. And that's what that superscripted O will mean. It doesn't, frankly, matter what temperature and pressure and molarity is involved in SATP. For you right now, just know that those are the temperatures and pressures and molarities that SATP pertains to. Okay, so we're on page 213 now of our ebook, 213 of our ebook, and we're in this section titled The Use of Heats of Formation, which we don't quite understand yet. We're looking at this problem here, and at first it looks like a Hess Law problem, and in fact it is. And in fact all this stuff is interconnected. Heats of formation, Hess Law, bond enthalpies, all connected. If we notice these three equations, like we know from Hess Law, are if they're added algebraically and things are canceled, give us this overall reaction below. Notice that carbons would cancel, hydrogens would cancel. What else do we have canceling? That's it, leaving us with methane and two oxygens, forming carbon dioxide and water. Yikes, not writing well today. And if we sum those three delta H's on the right, we get the overall enthalpy of reaction. So again, looks kind of like a Hess Law problem, but in a moment it won't. Let's just take a look at what all these abbreviations mean. Delta H we know means heat of or enthalpy of, and we know this delta H naught means that this reaction is happening at standard state conditions, 25 degrees Celsius, 1 atmosphere of pressure. And it's just a regular delta H because it's just a regular reaction. Maybe you could go delta H decomp down there, delta H de comp because it's a decomp reaction, but let's not. For these next two, though, they say delta HF, and that's the abbreviation for a heat of formation, because what these are formation reactions. Carbon dioxide, a molecule, is being formed in its standard state at 25 degrees Celsius. Carbon dioxide is a gas, and it's being formed from its two elements in their standard states. It's being formed from solid carbon. Carbon is a solid at 25 degrees Celsius and at 1 atmosphere of pressure. And oxygen is always diatomic, and it's a gas at 25 degrees Celsius. So carbon dioxide is being formed from its elements in their standard states. That's why this is a heat of formation. So is the third reaction a heat of formation. Water at room temperature, 25 degrees Celsius, is a liquid, and it's being formed from its two elements, hydrogen and oxygen, which at 25 degrees Celsius are gases, and they're both diatomic as well under standard conditions. Technically, this would not be the heat of formation you'd see for water in your book, because the heats of formation in our book are for 1 mole of a substance being formed from their elements in their standard states. So this value in the book would be divided in half, because this shows 2 moles of water, not 1. The reason why we have 2 here is so everything adds up nicely to give us this overall reaction. So the last 2 reactions are heat of formation reactions, but the first one isn't. Although, and we're going to go to a whiteboard here in a moment, if we flip that first reaction around and see carbon and hydrogen, elements in their standard states, forming methane, a gas, in its standard state, the first reaction would be a heat of formation reaction were it flipped. And that's what is significant about this and what I want to point out to you as we go to our whiteboard. So ignore for a moment this reaction in black at the top and focus on the blue, green, and red reactions. These are the same 3 we just saw, where when added up, they give us this overall reaction, whose enthalpy is the sum of these 3 enthalpies. So everything except for the reaction in black is what we just saw. The reaction in black is this first reaction that is in blue flipped around. A moment ago I said if we'd flipped that first reaction around, we would have an enthalpy of formation, because methane gas is being formed from its elements in their standard states. And when I flip a reaction around, the enthalpy value has to change. So instead of 75 kilojoules per mole, we've got negative 75 kilojoules per mole. Now we have 3 heat of formation reactions. The first one in black, we're skipping blue, the green one, and the red one. Those are 3 heat of formation reactions. And as you know, this overall enthalpy for this reaction came from summing the enthalpies of the first, second, and third reactions. Blue plus negative green plus negative red. And all of this is my attempt at helping you understand why this formula down here makes sense. Ultimately, you just need to know to use this formula when you want to find an enthalpy of reaction from heats of formation. But this whole little bit here is helping you explain why this works. Well, notice that carbon dioxide and water in this overall reaction are products. Carbon dioxide and water are products. And notice that in reaction 2 and reaction 3, they were produced. They were produced. And that when we found this overall enthalpy, which is negative 891, we took the heat of formation for water, a product, and it was negative, added it to the heat of formation of carbon dioxide, another product. We added these two numbers together. Yeah, they were negative to get the overall enthalpy, and we added it to 75. Carbon dioxide and water were products, and we used their heats of formation in Hess's law. But methane is a reactant. Methane is a reactant. And in this blue reaction up here, we did not use its heat of formation when we added it to negative 394 and negative 572. We used 75 kilojoules, which is the opposite of its heat of formation. But if we had had its heat of formation, right, if we'd had methane's heat of formation, which is the opposite of blue reaction, all we really needed to do was switch its sign to become from negative 75, 75, and when that's added to negative 394 and negative 572, we get the overall enthalpy of reaction. So what actually we were doing to find this overall enthalpy, sure using Hess's law, but now thinking of heats of formation, is the heat of formation of carbon dioxide, a product, which is right there, was added to the heat of formation of two waters, which was right there, and that was from that was subtracted the heat of formation of the reactant methane, which is up here, because there's the heat of formation of methane. And we had to switch the sign. From negative 75, it went positive 75. So it's the heat of formation of the two products minus the heat of formation of the reactant, turning negative 75 into positive 75. Now, oxygen is omitted from this because elements that are in their standard states already, and oxygen is in its standard state already, it's O2 and it's a gas, have heats of formation of 0 because they're already in their standard state. It doesn't take any energy to form them. So the overall equation we will use to find an enthalpy of reaction from enthalpies of formation is the sum of the heats of formation of the products, in this case it was carbon dioxide and water, minus the sum of the heats of formation of the reactants, which in this case was only methane because oxygen is an element already in its standard state. And that is, once again, negative 572 combined with negative 394, those are the products, minus the heat of formation of methane minus negative 75, which is really adding 75 to it. So my hope is that that gives you some context for how this equation works. But if that didn't make sense, as long as you trust that this equation down here works and can follow me with a sample problem, you'll be in great shape anyways. So we've flipped our page again. We're on 214 of the ebook looking at table 4.5.1, a table of heats of formation of a variety of substances. Notice these all have no coefficients in them because by definition heat of formation is the energy change or enthalpy change associated with forming 1 mole of a substance in its standard state from its constituent elements in their standard states. So NH3 would have been formed from N2 and H2s. Notice that all the units are kilojoules per mole. That's typical. And notice that while many of these are negative, forming many molecules is exothermic, there are a few substances that have endothermic heats of formation. So we're now on page 215 of our ebook, and we're going to do practice problem 1 here on page 215. It's telling us to use the values we just saw in that table, 451, to solve this. And it says to determine the enthalpy change for each of the following reactions. In a problem that you're given on a test, not that it's all about tests, it should be really clear to you whether you're using Hess's law or heats of formation or bond energy values. If it's a Hess law problem, there'll be a series of reactions that will add up algebraically the overall reaction. They'll be in the problem. If it's asking you to use heats of formation, it'll either say so or it'll give you a table within the problem with heats of formation. So is that true for bond enthalpies? It'll either tell you use the bond enthalpy values or it'll give you a table. So it's meant to be pretty clear which method to use. All right, so we're going to go back to our whiteboard to solve this. Here's our equation again. The enthalpy of reaction under standard state conditions is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. This equation could make sense based on what we did, but it could also make sense in terms of what we know about sign conventions for enthalpy. If products are formed, then it makes sense that we use their heats of formation values as they're published. We don't switch their sign. Products are formed, and therefore, when we're looking up the heats of formation on a table, their signs are valid because they're formed. Reactants aren't formed. They're broken apart. which is why that negative sign is there, because we have to think of the opposite of them forming as reactants, and therefore it's the opposite change in energy than the one we see on the table. Like bond energies, the sign should make sense. But remember, bond energies is reactants minus products, because bond energies are about reactants bonds breaking and not products. So just think about that. Why that negative sign is in front of reactants this time, but it was in front of products for the bond enthalpies. All right, so this just becomes some math. We're going to focus on our products first. We're going to find C2H6 and then CH4 in the heats of formation table. And because there's 1 mole of each produced, I don't need to multiply either of those values by any coefficient. And there they are for my products. Here is C2H6's heat of formation, negative 84.7 kilojoules per mole, added to methane's heat of formation, added to a negative 74.9 kilojoules per mole. So now I'll go to my reactants. C3H8 and H2 both have coefficients of 1, so I also, for those, don't need to do anything to the numbers. Of course, though, I've got to put a negative sign out front before I do all of my adding. So I find C3H8 on my heat of formation table. Made a little boo-boo. Find C3H8's heat of formation on the table. It's negative 105. And I look for hydrogens, but it's not there, because hydrogen is already an element in its standard state. Hydrogen is diatomic, and it's a gas at SATP, so I won't find it there. It's 0. I could add 0 to negative 105, but I don't need to. Elements in their standard states have enthalpies of formation of 0. So here's my math. I just need to add all these numbers up, and that'll give me my final answer. And I got negative 54.6 kilojoules per mole. You may find, once you get the hang of this, and hopefully you do already, that these heat of formation problems, determining enthalpy from heat of formation, are some of the simplest mathematically. All right, I'm going to do one more with you. I feel like you have the hang of it. You could leave now, but I'm going to do one more with you. Suggest you pause your video, check your work against mine, and then that'll be it. So we're going to do 1B together. 1B on this same page, 215 of your ebook, and we'll pop over to the whiteboard to solve it. So here it is. I've written out the reaction, the equation. The enthalpy of this reaction under standard state conditions is equal to the sum. Oh, my triangles are getting worse by the moment, of the heats of formation of the products minus the sum of the heats of formation of the reactants. Give this one a shot. Come on back, check your work against mine, and then we'll shut this party down. All right, let's see what I got. So I started with the products, I always do, and I found SO2's heat of formation on my table, which was negative 296.8. Because there's 2 moles, I've got to double that. So 2 times negative 296.8 is SO2, plus 2 moles of water as well, times its heat of formation, which is also negative. Put all that in brackets. And then minus, that's the minus from here, the sum of the reactants, which is H2S, which there are 2 of. So that's H2S's heat of formation. And then again, oxygen is an element already in its standard state. Oxygen is diatomic, and it's a gas. So its heat of formation is 0. We don't need to bring it in. And the grand total is negative 1124.8 kilojoules per mole. Highly exothermic reaction, the combustion or oxidation of hydrogen sulfide gas into sulfur dioxide and liquid water. So that is it, folks. Lecture 14, Part 2 is over. Mr. Johnson signing out after 10.5 hours of sitting in this chair. The sun has set in Sammamish. I wish you well. I wish you a good whatever it is that is upon you for the rest of your day, and I'll see you soon.